Okay, so good morning, everyone. I'm Luca, postdoc at the INFN of Rome. Um, in this presentation, on behalf of the LIGO Virgo Cagra collaboration, I will describe how we can search for continuous gravitational wave from known pulsars and what is also the multi-messenger approach of this kind of search. Let's start from the gravitational wave that are small perturbation in space-time, and these waves are transverse to direction of propagation, and you can see the effect of the passage of a gravitational wave on a test of ring masses in this picture. You see the effect of the plus and of the cross polarization. And basically, the effect is a differential change in the distance between these free falling masses. And the ground-based detectors are interferometers that are good transducer that converts the displacement into an optical signal. This is a picture of the advanced Virgo. It's the interferometer in Italy, near Pisa. There are then other two ground-based detectors in the US that are the two LIGO, and then there is also the Kagra, that is the underground Japanese interferometer. And the output of the detector is expressed in terms of this strain, that is the ratio between the differential arm displacement, so it's difference between the displacement of the X and of the Y arm, divided by this mean length of the two arms. And to show the sensitivity of our detector, we use the amplitude spectral density. That is, in other words, the distribution of the square root of the power as a function of the frequency. And so you can see the sensitivity of the Virgo detector and of the two LIGO during the last observing run, that is the O3 run. And the sources for ground-based detector, of course, should be relativistic, compact, and with an internal time-varying quadrupole motion. And there are four main groups of sources, and they can be divided according to the time scale of the signals, and also if we can model the waveform, the expected waveform. And so far, we have detected the merger of black hole or neutron star. This is a picture of a model of the waveform. As you can see, the time scale here is of the order of the fraction of second, and you see the spiral phase, the merger, and then the ring down. While in this plot here on the right, there is the number of cumulative events that we have detected during the 3 observing run. And so it's also clear here the improvement in the sensitivity. And we have so far almost 90 detection of merger of black hole or black hole, neutron star, or also the famous merger of the two neutron stars with the multi-messenger counterpart. These are the results until O3 data, but a few months ago we started the O4 run, and so there are now actually one detection every 2 or 3 days. And this plot, there is the observing plan for the LIGO, for Virgo, and for Kagra. This number here are a different metric to show the sensitivity. It's the binary neutron star merger. And you can see that now the two LIGO are working, and Virgo will join hopefully the next year, the O4 run. The topic of this talk is quite different from the detection that we had from the merger of the neutron star, because the topic is the signal emitted by spinning neutron stars, the so-called continuous signals. As you can see, these signals are long-lived and with well-known waveforms. Indeed, as I said, the sources are spinning neutron stars with a non-axisymmetric mass distribution. The time scale is of the order of months or even years. And these signals in the source reference frame are almost monochromatic, with the gravitational wave frequency that is proportional to the source rotation frequency. But the amplitude of this kind of signal is expected much weaker than the one that we have detected from the merger of black hole and neutron star. In general, you need at least 8 parameters to define a continuous signal. The rotation frequency, how this change in time, and then the sky source position. Then you have the amplitude, the initial phase, and the polarization parameter that define the gravitational wave. Then, according to our knowledge about the source, this means our knowledge about the rotation parameter and the sky position, we can perform different analysis, different searches for this kind of signal. And in this presentation, I will describe in detail the targeted search that, as you can see from this picture, targeted searches are the most sensitive analysis that we can perform. Here you have the sensitivity as a function of the computational cost for the different searches, because the targets in this kind of analysis are known pulsars, so are well measured in the electromagnetic spectrum. And this means that you can constrain the rotational parameter and the sky position, and you can perform a single template analysis. Then you can relax the assumption on the source, or maybe you don't have the information about the source, and so you perform different kind of analysis. But these are multi-template search because you have a parameter, space parameter to explore, and so you increase the computational cost of the analysis, but decrease, of course, in sensitivity. And from all three data, we had 16 collaboration paper on the different kind of analysis and targeting continuous signal. Let me say here that we have no detection of continuous signal from any of the searches that we have performed. As I said, the topic of this presentation is a targeted search, which there is a strong multi-messenger approach, because we need the electromagnetic information to constrain the source parameter. And so, in other words, the targets here are pulsars that are observed in the radio, in the X-ray, and the gamma-ray band. Up to now, we know in our galaxies almost 3,000 pulsars, but only a small fraction of these are in the sensitivity band of ground-based detectors. The targeted searches are the most sensitive analysis that we can perform, because since we know the source parameter, we know also the shape of the signal, and so we can integrate the signal over time in this way, using full coherent method that maximize our sensitivity. And in this box, there is the expression for the minimum detectable amplitude for our detectors that is proportional to the sensitivity. This is the amplitude spectral density, and it's a function of the frequency, and it's divided by the square root of the observation time. Then why we search for continuous signal? Because a future detection can return important information about, for example, the physics of neutron stars, let's say the equation of state. But of course, this depends on the emission scenario, because there are different models that entail the emission of a continuous signal. For example, the simplest model considers the source as a rigid, steady rotator with a small deformation on the crust. It's the so-called bumpy neutron star model, in which the signal at the source is monochromatic with the frequency that is exactly twice the rotation frequency of the source. This is an expected value of the amplitude in terms of the strain for fixed value of the frequency, of the distance, of the moment of inertia, and also of the ellipticity. The ellipticity is the degree of deformation of the neutron stars. It can be approximated by this ratio, in which you have the deformation of the radius divided by the radius itself. This means that generally a neutron star has a radius of the order of 10 kilometers. So if you have an ellipticity of 10 to minus 6, means that the deformation that we are looking for is of the order of the centimeter and even below. Then we can set a theoretical upper limit to the amplitude, because the pulsars are observed to spin down, and so to lose energy. And we can assume that this loss of energy is completely due to the emission of gravitational wave. Of course, this is a strong assumption, but it allows to set a theoretical upper limit to the amplitude that has this expression. So it depends on the inverse of the distance and then of the ratio between the spin down and the rotation frequency. In the last part of the slide, there is a sketch of the signals. As I said, in the source reference frame, the signal is almost monochromatic, but you have to take into account the spin down of the pulsars. But then the detector is on Earth, and so you have to take into account the Doppler effect due to the orbital motion around the sun. And at the end, the detector, there is a residual modulation due to the sidereal motion of the Earth. Let's say a modulation that depends on the response of the detector to the coming gravitational wave. And this response splits at the detector the signal in 5 frequencies. You have the central peak at twice the rotation frequency, and then you have 4 sidebands that are linked to the angular sidereal frequency of the Earth. To correct for the spin down and for the Doppler effect, you need to know the phase model. So, in other words, you need an accurate measurement of the source parameter. And one of the way that you can demodulate the signals, so you can correct for the Doppler and for the spin down, is the use of the heterodyne correction. In this correction, you multiply the output of the detector that here is indicated as an expected signal plus some noise for this exponential factor. And in this phase, you reconstruct the modulation of the Doppler and the spin down. Indeed, this is the sum of 3 terms. You have the spin down, then the contribution of the Doppler effect, and then you have also, if the pulsar is in a binary system, you have also Doppler effect due to the orbital motion of the pulsar. Then usually matched filter techniques are used, but the longer is the signal, and we can say the longer is the observation time, the more sensitive is a matched filter to possible offset in the template parameter. This means, for example, that if you have a best fit value, for example, for the orbital period for a pulsar in a binary system, that has an offset, a mismatch, you just add here a phase, and so you are not correct as you need the Doppler and the Doppler effect. Then we define high-value targets, the pulsars in which the minimum detectable amplitude that we can detect for the particular targets is close to the spin down limit that we have defined in some slide ago. And this is a classic PP dot diagram in which the red region is forbidden for ground-based detector because we are sensitive above 20 Hertz. And so there are the millisecond pulsars that we target, but in general, these pulsars have a small spin down, and so that is well below the current sensitivity for our detector. And then there are some young pulsars like the crab or the vela that have large spin down and low frequencies, and these in general have highest gravitational wave spin down, and so are main targets of our analysis. And these are the results of the last targeted search, in which we have no evidence of a continuous signal. The results are described in this paper, in which we have analyzed more than 200 of known pulsars using the data from the last observing run, DO3 data, and also to constrain the source parameter, the electromagnetic data from different telescopes. And we used the Bayesian analysis for each of these 200 and more pulsars, and other 2 independent Papillon only on the set of high-value pulsars. High-value pulsars, as I said before, are the pulsars in which the upper limit, let's say, on the amplitude is below the theoretical spin down limit. And in this analysis, we have 20 pulsars with an experimental upper limit that is below the theoretical spin down limit. In this plot on the right, there are the upper limits on the amplitude that are the blue stars that are compared with the sensitivity of our detector, that is the pink line, and with the theoretical spin down for each target that are the gray triangle. And the dashed line shows the high value pulsars. Let me focus on these pulsars in which with this upper limit on the amplitude and with an estimation of the distance of 0.1 kiloparsec, constrain the ellipticity of the order of 5 times 10 to minus 9. This means that the deformation, or let's say the mountain or the crust of neutron stars, is below 30 micron. Of course, for the model that we are looking for. We perform also different kind of analysis for pulsars. First of all, the narrow band searches, in which you relax the assumption between the gravitational wave frequency and the rotation frequency. So you allow an unknown mismatch between the rotation parameter and the gravitational wave parameter. Of course, you decrease in sensitivity because you have a frequency band to explore in our data. And so let's say you have a trial factor that decreases your sensitivity. And this is the last search on O3 data and on targeting 18 isolated pulsars with the spin down limit that has been surpassed for 7 of these pulsars. Then we have also an analysis targeting 20 accreting millisecond X-ray pulsars, but performing again a narrow band analysis. Then we can perform also post-glitches search, because we can search for long continuous wave-like transient, because there are models that suggest that post-glitches you have some changes in the quadrupolar moment, and so the emission of continuous wave, at least for a small period. We searched also for R modes. This is a different emission model, because R modes are oscillation of the inner fluid of the neutron stars. And so there are some models that entails a different relation between the gravitational wave frequency and the rotation frequency. And we searched for this pulsar that is the big glitcher, and it's basically an extension of the narrow band analysis, but for interglitch quiet periods. There are also efforts outside the LVK. There are some groups that are not in the collaboration that also analyze and search for continuous signal. For example, in this paper, you have the analysis from some Fermi targets that we have known in our analysis. And at the end, we also perform so-called directed searches, in which you know the sky position of the source, but you have no information about the rotation parameters. And of course, these are less sensitive analysis, but allow to targets, for example, supernova remnants or some spot in the sky, like the galactic center or particular globular cluster. And I would like to conclude with this slide. This is what we continuous wave analysts need from the electromagnetic point of view, because for our analysis, the much we know about the source parameter, the better is the sensitivity, and also less is the computational cost. And so what we need is high precision ephemerides for each of the target to avoid the phasing, as we have seen from the phase model. Then update measurements of the pulsars that cover the current observing run and so that match with our data. Then we need also radio observatories that are able to monitor the radio pulsars that we analyze, and of course mainly for the high value targets, so the young pulsars. For the different analysis that we can perform, also we need the glitch alerts and relaxation time measurements. And of course, the discovery of new pulsars in all the electromagnetic bands for new targets, for all the different kind of analysis that we can perform. And these are my conclusion. The take-home message, I think that it's continuous wave analysis have a strong multi-messenger approach, and there are a lot of analysis that are basically depends on the electromagnetic observation that constrain the parameter space that we have to explore. I have described the target search that are the most sensitive analysis that we can perform. So far, we have no evidence of a continuous signal in our data, but the O4 run has started a few months ago, and we will start the analysis of the first months, and so we hopefully will have the first results on the targets and on some other specific paper in the next months. So thank you, and let me know if there are questions.
Any questions for Luca?
Online, no. In the room, any questions? We have time for a couple if anyone has anything on their mind. All right, I guess not. It must have been extremely. Oh, here we go. Roland, go ahead.
Hey, Luca. Nice talk.
Hi.
So, with Virgo, there's always the question: how are things going with the current status of the detector? And the other
For the
thing,
Virgo side, you say?
yes, yes, and
Yeah,
yeah, go
we are a
ahead.
bit in delay, but there are great efforts from the characterization team and from the instrumental side. We had some problems with the mystery noise that decrease our sensitivity because the target for O4 was of 80 megaparsec, but we had some problems with the upgrade because there were from O3 and to O4 we had a lot of upgrade in our instrument, and so now there is a mystery noise in the central part of the spectrum between 16 and let's say 100 hertz, and this decreases a lot the sensitivity of our detectors. But in the last observing plan, we have decided to join the O4 run with any sensitivity with the start the O4B, because as you can see here, LIGO will have we'll have a stop during January and February, and then we'll start in March. And so Virgo will join with any sensitivity in March.
Okay, that's actually great news. The other thing I wanted to ask is, um, so sorry, okay. The other thing I wanted to ask is, how rapid do you need the triggers to be from, and do you expect the triggers to come from radio to the gravitational wave detection end, or to go the other way around for this continuous?
I don't say trigger because we need the observation. For example, for target searches, we need the observation of the pulsars that matches with the current observing run. So for example, if we analyze O4 data, we need timing solutions that are updated with the start and the end of for run. Because the idea here is that you need the source parameter to have the shape of the signal and to integrate the signal over long time periods. And this is the main point that increases your sensitivity. Then yes, you can perform different analysis as you can as I described, for example, for after glitch on some pulsars, and so in that case you need glitch alerts, for example. Thank you for the question.
Yeah, sorry, I was thinking of glitches and not.
Okay, yes.
Yeah, you're right. Okay, that's
well,
good. Thanks.
if you have these these alerts, then we can perform the analysis the faster that we can. So yeah. Then it depends also the nature of the glitches on the source and the type of the analysis that you can perform, because basically these are continuous wave-like transients. You have an emission just for a short period after the glitches, but the data are always there, so we can look whenever we want to the end of analysis.